The mode transfer or propagation matrix describes the amplitude and phase of the couplings between all the spatial and polarization modes a fiber supports. It completely describes the propagation of light within the fiber for a given wavelength and can be used to map any input field to the corresponding output field. If you know the transfer matrix and you know what you're coupling into the fiber, then you know what you're going to be getting out. In the context of transmission experiments, that's the information you'll need in order to recover your channels after propagation through the fiber. However, it's got more general physics applications as well, because you know all there is to know linearly about the fiber. You can use it to do imaging through a multimode fiber, which is like imaging through turbulent media. Because if you're seeing some pattern at one end of the fiber, you know what the pattern must be at the other end which caused it. Or in the reverse direction, if you want to make a particular pattern appear at the other end of the fiber, you know what you need to couple into the fiber. There's a few different schemes around for measuring some or all of the mode transfer matrix, and I don't have time to compare them all here. But most techniques don't give you the entire matrix, either because you measure less elements than there are modes, or because there's particular phase relationships that aren't meaningful or aren't of interest. The system I use is based on spatial light modulators, and it can measure the entire matrix where every aspect of every element has physical and practical significance. So an SLM allows you to generate or detect an arbitrary spatial mode in an arbitrary polarization. This is the system I use for mode multiplexing. The beam or beams from an array of single mode fibers come into the polarization diversity optics, which splits it up into two beams representing orthogonal polarizations in the input-output fiber, but which are now both aligned with the polarization required of the liquid crystals in the SLM. The SLM can hence address either polarization independently. Now, I generally show it as if the SLM is a transmissive device for reasons of clarity, but in reality the SLM is reflective and the inbound and outbound optics are stacked on top of one another like so. After reflecting off the SLM, the two orthogonally polarized beams are recombined and focused onto the output multimode fiber. So in practice it plays out like so. Gaussian beam comes in some particular polarization, the phase mask converts it to a higher order mode which is coupled into the fiber. Along the length of the fiber, that mode undergoes mixing as per the mode transfer matrix, and it arrives at an identical system at the receiver which plays out the process in reverse. Mode comes out, masks convert both polarizations back to Gaussians and couple them into the output single mode fiber. By displaying phase masks for each mode one at a time at the transmitter and displaying masks for each mode one at a time at the receiver and measuring the coupling into an output single mode fiber, it's possible to build up the amplitude of the elements of the mode transfer matrix. So this is an example of a 2 meter piece of fiber, 3 spatial modes per polarization. As you can see, the degenerate polarizations of the fundamental mode mixed together, and the degenerate forms of the LP11 modes mixed together, and there's not a lot of mixing between the two mode groups. The SLM can also acquire the phase for each of those mode matrix elements, and it does that like so. Say for instance, we have this mode superposition arriving at us at the receiver in some particular polarization. It's a mixture of LP12 and LP31 modes. We want to know what the amplitude and phase of that beam is. And in the middle, we have the image plane, the plane of the phase mask, the plane of the SLM. And on the right, we've got the Fourier plane, the plane of the output single mode fiber. So the SLM displays masks for each of the basis modes and measures the coupling into a single mode fiber as per the previous slide. Now it knows the amplitude of each mode. Then it superimposes the mask for each of those modes with different relative phases to work out the phase of each mode. When the mask is conjugated with the beam, the coupling is maximized and you've completely decomposed that beam. This is how that plays out in the lab. Quickly flashes masks for each mode, then interferes the masks together, and the power fluctuates on the power meter, revealing the phase. So now we've got the amplitude and phase of each element in the matrix. And this is the 3-mode fiber from before. And if you multiply that matrix by its complex conjugate transpose, you can see that you get the identity matrix, verifying that it's a unitary matrix, i.e. that its conjugate transpose is its inverse. And for most purposes, in terms of measuring the properties of the fiber, that's all the information you need. However, as yet, the matrix is not entirely complete, as the phases along a column are defined, but the phases between the columns are not meaningful. That is, you know what the relative phases are of all the modes at the receiver if you launch one of the basis modes at the transmitter, but what if you launch multiple modes simultaneously? How will they interfere? You don't know that. The phases are currently defined relative to some arbitrary reference, and I usually just use whatever the strongest mode happens to be for a given launch. Another way to think of it is that you know all the relative phases between the modes in the forward propagation direction, but not in reverse. Some techniques in imaging get around that by actually propagating light backwards through the fiber to measure the matrix, and then propagating light forwards to generate the pattern thereafter, or by using an external phase reference of some kind, such as swept wavelength interferometry. This technique doesn't use an external reference and it doesn't propagate backwards. The laser is always on the same end of the fiber. Instead, it sends a reference mode along the fiber itself, which is used to define the phases of all the other modes. It can be any mode or group of modes you want. Here I'm going to show the fundamental. So the system launches both the mode of interest and the reference mode simultaneously in superposition, couples them into the fiber. They arrive at the other end after some mixing. Now each of those modes have their own detection phase mask pattern. So you interfere those two masks together to work out their relative phases. And now the entire matrix is defined in a meaningful way. It also means that because all the light for all the modes has traveled through the same fibers, you can use a low coherence source, as you don't have to be worried about path length matching or anything like that. I'm using a 0.5 nanometer filtered and polarized ASE in these demos. Another good thing is that all the phase values are defined with reference to the plane of the SLMs, which is where you're doing the measurements, but it's also where you generate the modes. So once you have the information you need, you can use that information directly to launch particular mode superpositions of interest, where all the phase values are correctly defined. So putting that all together for a multi-mode fiber, in this case I'm using a standard piece of OM4 grade 50 micron core graded index patch cord, about 2 meters long. Theoretically that has 110 modes total, 55 modes per polarization, and that extends from the fundamental mode up to the 10th degenerate mode group, which has modes like LP91, OAM, spin 9, that kind of thing. This is the amplitude of that measured matrix. You can see it's pretty sparse, with most of the amplitude scattered around the diagonal. Modes mix mostly with modes of similar propagation constants, so power in the white squares along the diagonal represents mixing within a mode group, i.e. mixing between modes which are theoretically almost degenerate. You can also see that for most practical cases, you don't really need to measure the entire matrix. There's a lot of zeros in there, and you've got a pretty good idea where those zeros are going to be before you start. If you take the singular value decomposition of that matrix, you can get the eigenvalues for each of the 110 potential channels. There's a slope there, which decreases steadily until about the 9th mode group, at which point it dives off a cliff as the modes become cut off. Now I believe this mode-dependent loss, with the exception of those higher order modes, is more a measurement of the quality of my mode multiplexer, demultiplexer, than the fiber itself. Those lower and middle order modes should be heavily bound. Shouldn't be much loss. In particular, when you're measuring this matrix, you have to make sure that you get the phase values of the modes spot on, or you'll start to accumulate MDL. That's usually the trickier thing. Amplitude's not too bad. Now, with the full matrix acquired, we know how every input maps to every output, and we can start to make particular patterns show up at the receiver. For example, say I want to make an LP05 mode arrive at the receiver in some particular polarization. It's one of the highest order modes the fiber supports. Given the measured mode transfer matrix, I know that I must launch this mixture of amplitude, phase, and polarization at the transmitter. That's a simulated image. There's no observation camera at the transmitter. So you display masks on the transmitter SLM designed to generate those fields. And this image is observed on the polarization diverse imaging system I've got attached to the receiver. And here's some other examples. I've got an OAM spin 8 horizontally polarized at the receiver. It's a bit splotchy because one of the LP81 modes has more loss than the other LP81. I've got a vertically polarized LP22 mode, and if you want to get a bit fancy, you can also make different modes come out different ports of your beam splitter, the receiver. So here I've got an LP04 coming out horizontally polarized, and an LP42 coming out vertically polarized. And that's it. Thank you very much.